So hi everyone, welcome to my new video on the topic of elastic potential energy. Okay, now first of all we need to understand why it is called potential energy. Okay, see, potential energy, it is the energy possessed by body by virtue of its position or configuration. Configuration means shape. Okay, so that means if there is a change in position of a body or if there is a change in shape of a body, then it involves potential energy. Okay, so suppose we have a rod. Okay, and this rod is fixed rigidly at this end, and from this end, this is the free end. So from this free end we are applying a force F. Okay, now because of this application of this force, suppose it undergoes an elongation. So initial length is L. Okay, and suppose delta L is the elongation. Delta L is the elongation. Okay, so the length changes from L to L plus delta L. Okay, so obviously there is a change in shape. Okay, so in order to change this shape of this object, you are applying some force. That means you are spending some energy. Okay, now that energy is converted into elastic potential energy of this system. Okay, so we are going to calculate the expression for elastic potential energy. So obviously this elastic potential energy, it will be equal to the work done in deformation. That is to increase the length from L to L plus delta L. Okay, now suppose, so initial length is L and final length is L plus delta L. Okay, now suppose there is an intermediate stage where the length is L plus X. That means initially here elongation is 0, here elongation is X, and here elongation is delta L. Okay, so we know that now if we are talking about this intermediate stage, we know that Young's modulus, it is a ratio of longitudinal stress divided by longitudinal strain. Okay, so this is Young's modulus equal to, suppose F is the force and cross sectional area is say A, longitudinal strain, so change in length by original length. So suppose intermediate stage, so change in length is X, so this is X by L. Okay, so I can write this as Y is equal to F into L divided by A into X. Okay, or this implies F is equal to Y A X divided by L. Okay, so this is the expression for force. Okay, so now small work done dW to elongate this rod through additional distance dx. It will be dW equal to F into dx. This is the small work done. Okay, so this is a small work done for elongation dx. This is the additional elongation dx. Okay, so dW, it is equal to this quantity, force is YAX by L dx. Okay, So the total amount of work done can be obtained by integrating this expression, correct? So integration from where? Initial elongation was 0, work done was 0. Final elongation is delta L, total work done is W. Okay, so here what is changing? Value of x is changing, and because of change in value of this x, the work changes from 0 to W. Okay, so this is how this limit is given. So dw integrate W, so dw integration is W, limit is 0 to W. So this is equal to ya by L. So this being constant, I have taken it outside the bracket, and integration of x dx. Now integration of x power n dx, it is equal to x power n plus 1 divided by n plus 1. Okay, so this is x power 1, so this is x power 1 plus 1 divided by 1 plus 1. So this is basically x square by 2. Okay, so this is 2 x square by 2. Okay, now after substituting this limit, so upper limit minus lower limit, it is equal to ya by this 2 I am taking outside, twice L, upper limit delta L square minus 0 square. Okay, so we have the final expression for work done. It is W is equal to ya delta L square divided by twice L. So this is the expression for work done. Now this work done, this is the work done by external force. Now this work done, this is the work done in producing an elongation delta L. So this work done gets stored in this system as potential energy, as elastic potential energy. Okay, so this work done gets stored as elastic potential energy. Okay, now symbol for potential energy is U, capital U. So that means this quantity it is equal to U. Okay, so this is the expression for potential energy. Okay, now we can write this expression in different forms, but this is the final expression, this is the derivation. Okay, so I hope so this is 0 to W. So you need to understand how this limit was given. Okay, then this part, calculation part, and this final result. Okay, so how to write in this equation in different forms? So now we have, see, U is equal to ya by twice L delta L square. Okay, see, I have written this expression for force when the elongation was x. So if the final elongation is delta L, so this x can be replaced by delta L. So this is the expression for force. Okay, so that is ya delta L by L. So I can write this as ya delta L by L. Okay, 1 by 2 delta L. This can be written like this. Okay, so why I am writing like this? Because this term can be replaced by force. So we have U is equal to half F into delta L. Okay, so this is another form of elastic potential energy. Okay, this is the stretching force and this is the elongation. Okay, so I can write this as U is equal to half into stretching force into elongation Okay, acha. Now there is another way of writing this. Say I can write this as U is equal to 1 by 2 F delta L. Now if I divide by A and multiply by A. Okay, so now this quantity, this is stress, okay, and if I divide this by L and multiply by L, So this delta L by L, this is strain. This strain, and A into L, area and cross section area into length. What is this? This is volume. Okay, so potential energy is equal to half into stress into strain into volume. So this is another form of writing the expression for elastic potential energy. Okay, now this quantity, energy per unit volume, this is called energy density. Energy density, it is denoted by the symbol small u. Energy is, potential energy is capital U, and energy density is small u. Okay, so this u by volume, so energy density is small u is equal to half into stress into strain. Okay, so this is the expression for energy density. Okay, this is energy density. Energy density. So if energy density is given, if you multiply energy density with the total volume, you will get the total elastic potential energy. Okay. So this is the complete derivation of elastic potential energy. Okay, and you can write this expression of elastic potential energy into these various forms. Okay, so you need to understand the expression for elastic potential energy and also energy density. Okay. Next, one term we need to know is elastic after effect. Elastic after effect. Elastic after effect means it is a slow process. See, if an object is deformed, okay, if an object is deformed and it regains its original shape after some time. So that is, suppose this is an object and it is deformed like this by application of external force. It is bent like this, and when the external force is removed, then it slowly acquires its original shape. Okay, so this slow process of regaining the original shape is called elastic after effect. Okay, and now the time, this time gap of this deformation and then again acquiring the original shape, this time gap is called relaxation time. Relaxation time. So this is elastic after effect. Then there is another term we need to understand is elastic fatigue. Elastic fatigue. Elastic fatigue is like if an object is subjected to alternate stress and strain, then it loses its elastic property and then finally it breaks. It is like, suppose you have a metallic wire. Now you might have seen that if you bend the wire continuously, then the wire may break. Okay, so that process is called elastic fatigue. It is for this reason, like bridges, wooden bridges or not normal bridges, see, they are declared unsafe after some years of operation, say 50 years, 100 years. Okay, because this bridge also undergoes elastic deformation. Okay, when a heavy vehicles moves through a bridge, it undergoes some kind of elastic behavior. It oscillates, moves like this. Okay, so because of this alternate stress and strain, because of this application of force and the removal of force, it undergoes a loss of strength, and finally after some years, not some few years, in space 50 years or 100 years, it loses its all elastic properties and then it is unsafe for use. Okay, so that property is called elastic fatigue. Next topic is elastic hysteresis. Now see, basically see, I have drawn a graph of stress versus strain. Okay, this is strain. Now the graph starts from O, takes the path OAB. So when the load is applied, it takes the path OAB, and when the load is removed, it takes the path BCO. Okay. Now, what is the importance of this graph? See, First of all, see, when the load is applied, if it is taking path OAB, now when the load is removed, it should come along the same path BAO, but it is taking the path BCO. Okay, now what is the implication of this? See, basically stress strain graph, if you calculate the area under the stress strain graph, it basically gives you the amount of work done in producing a certain kind of stress, okay, or producing a certain kind of strain, or producing some certain kind of deformation. That is what we have learned about elastic potential energy. So that can be calculated by calculating the area under the graph. Okay, now if you see here, first case, we need to calculate the area under this curve. Like this is OAB. So you need to calculate the area of this part. Okay, but for the second part, means this, when the load is removed, the graph is taking this path BC. So you need to calculate the area of this part. Okay, area of this part. So obviously, see, area under BCO part will be lesser than area under OAB. So that means work done from O along OAB, it will be greater than work done along BCO. For this part, work done is more. So work done is more. So that means, see, when load is applied, you're doing work. Okay. When load is removed, you're releasing that energy. But the complete energy is not released. Less amount of energy is released. So that means some amount of energy is lost as heat. So that is the implication of this graph. Okay. So this graph is called elastic hysteresis. Elastic hysteresis. So next topic is bulk modulus. Okay, bulk modulus. Now bulk modulus, this is usually defined for fluids. Fluids means liquids and gases. Okay, it is usually, I'm not saying that it is not defined for solids, but it is usually defined for liquids and gases. Okay, now what is this bulk modulus? First of all, it is denoted by the symbol B for bulk modulus. So it is B is equal to volume stress by volume strain. Volume stress by volume strain. Okay, now this volume stress, stress is force per unit area, volume strain is delta V by V, but this force per unit area, see, since we are talking about fluids, that is liquids and gases, this force per unit area, this represents pressure. Okay, pressure, but actually this is change in pressure. Change in pressure. Okay, now see, force per unit area represents pressure, but I am calling it as change in pressure. Why? Because see, this is change in volume. A change in volume will produce a change in pressure. Okay, so I will write this bulk modulus B as this quantity delta P, this is the change in pressure, divided by delta V by V. Delta V by V. Okay. Now obviously, if you increase the pressure, the volume will decrease. Okay. Suppose this is an object, okay, and you are applying force from all sides. So obviously its size will decrease. Okay. So that means if you are increasing the pressure, the volume is decreasing. So that means, see, delta P, if it is you are increasing, delta V is decreasing. Delta P is the increase in pressure. Delta P is actually change in pressure, but if its arrow is going upward, that means if you are increasing the pressure, the volume, delta V is a change in volume. The volume is decreasing. So that means these two quantities should have opposite sign. Opposite sign. See, if we consider this delta P is decreasing, that means pressure is decreasing. So if pressure is decreasing, volume will increase. Okay, so these two will have opposite sign. That means if one is increasing, the other quantity will decrease. So if they have opposite sign, so that means if one is positive, other one is negative. One is positive, other one is negative. That means overall the quantity will be a negative quantity. So I am keeping a negative sign here. Okay. So this negative sign shows that delta P and delta V, they have opposite signs. Okay. So this is the expression for bulk modulus. This is the expression for bulk modulus. Okay. Now obviously this quantity has no dimension, no unit. Okay. This quantity has a unit of Pascal or Newton per meter square. So obviously bulk modulus will have a unit of Pascal or Newton per meter square. Okay. The reciprocal of bulk modulus, it is compressibility. Denoted by the symbol K. Okay. It is the reciprocal of bulk modulus. So that means K is equal to 1 by B. 1 by B. So 1 by B means it is equal to delta V by V with the minus sign divided by delta P. Okay. So this is the expression for compressibility. So if the unit of bulk modulus is Newton per meter square, the unit of this compressibility, it will be meter square per Newton, reciprocal of this. Okay. And how can we define compressibility? It can be defined as fractional change in volume per unit change in pressure. Okay. So this is fractional delta V by V is the fractional change in volume. So fractional change in volume per unit change in pressure. Per unit change in pressure. Regarding comparison of bulk modulus for various bodies or materials. See, bulk modulus, I told you, it is usually defined for fluids and fluids, that is liquids and gases, but it is also defined for solids, and in fact solids have highest bulk modulus. So bulk modulus of solids, it is greater than bulk modulus of liquids, and it is greater than bulk modulus of gases. This is the order of comparison of bulk modulus of various materials. Okay, so this is all about bulk modulus and compressibility. So next topic is relation between density. This is density. Okay, this is density, this is pressure, and this is bulk modulus. Bulk modulus. Okay, so what is the relation between these quantities? So basically, see, bulk modulus, it is minus delta P divided by delta V by B. Okay, so this is the expression for bulk modulus. This is by definition. Now density, it is equal to mass by volume. So mass equal to volume into density. Okay. Now this mass being constant, mass is constant. So what changes? Volume and density. Okay. So if I measure the change, then that means how will you measure the change? In mathematics, that is by differentiating. So this is a constant, so differentiating this I will get a 0. So this is 0 is equal to, these are two functions. So how I will differentiate? First I will keep this volume as constant and I will differentiate this. So this is delta rho. Okay. Then plus, then I will keep density constant, then I will differentiate this volume. So that is delta V. Okay. So this is rho delta V, it is equal to minus V delta rho. This I have taken to the other side. So this is delta V by V minus I am taking here, it is equal to delta rho by rho. Okay. So I can replace this quantity by this. Okay. So this goes over here. So this becomes B is equal to delta P divided by delta rho by rho. Okay. So I can write delta rho by rho is equal to delta P by B. Okay. So now if I add 1 on both sides, plus 1 plus 1. Okay. So this becomes rho plus delta rho by rho, it is equal to 1 plus delta P by B. Okay. So basically this is the initial density plus change in density, that is the final density. So this is the initial density and this is the final density. So I can replace this as initial density and this as final density. Okay, so I can write this as final density, it is equal to initial density rho I 1 plus delta P. This is change in pressure divided by bulk modulus. So this is the relation between density, final density, this is initial density, 1 plus delta P, change in pressure divided by bulk modulus. Okay, so this is one very important relation. Okay, why I am saying this as an important relation? Because if you go through your NCERT 9.13, so basically what is the question? What is the density of water at a depth where pressure is 80 atmosphere, given that its density at the surface is 1.03 into 10.3 kg per meter cube. Okay, so basically this question involves the concept which we have discussed just now. So this is water level. Okay, so here pressure is 1 atmosphere, here pressure is 80 atmosphere. Okay, and given that its density at the surface, so density at the surface rho initial, it is equal to 1.03 into 10.3 kg per meter cube, kg per meter cube. Okay, so there is a misprint, it is 1.03 10.3. Okay, and what is the density here? So final density rho final, this is asked. Okay, so based on the concept which we have discussed just now, so rho final, this is rho final, we need to find this rho final. Rho initial, this quantity, this is initial 1.03 into 10.3. Okay, 1 plus delta P, that is the change in pressure, 79 atmosphere, so 79 into 10 power 5 divided by bulk modulus of water. Now bulk modulus of water is 2.2 10 power 9, 2.2 into 10 power 9. Okay, so you have to simplify this to get the final result. Now if you simplify this, you will get the value somewhere close to this, because this value is very much less than 1. So final answer will be close to this, 1.03 into 10 power 3 kg per meter cube. Okay, so this is how you have to proceed to solve this question. So based on this video, please do write and these things on your own, okay, on paper, and then if you have any difficulty in understanding it, then please revert back to me, I will respond. Okay, and try out this question from the NCERT. Okay, though I have done it, but you should also try it on your own. This is question number 9.13. Okay, so with this I am signing off this video. Okay, my best wishes, good luck.